Let's look at this very typical rigid body equilibrium problem. The applied loadings acting on this beam is known, and we need to determine the support reactions at the fixed support A. Just like solving particle equilibrium problems, we start by sketching the free body diagram of the body. We know that we need to first isolate our object, therefore the wall needs to disappear. And then we need to note all external forces and moments on the diagram. But the problem is, we don't know what kind of support reactions we have at the wall. We will try our best to analyze the structure to fill that information in. First of all, we need to be clear that the body is in equilibrium. In other words, it is not moving. In fact, it is held static by the wall. Now, looking at the known applied loadings on this member, we see that there's a horizontal component of this force that will push the member to the left. Therefore, the wall must exert a horizontal force to the right in order to prevent this motion to the left. Then, because of the vertical component of this force, as well as this distributed force, causing the member to go down, therefore, the wall must exert a vertical force up in order to prevent this downward motion. Finally, the forces and the free 200 Newton-meter couple moment all cause the member to rotate clockwise. Therefore, the wall also must exert a moment support that is counterclockwise in order to prevent this rotational motion. Since this is a 2D problem, all motions can only occur within the xy plane, therefore there cannot be any other type of motion, and the wall will not provide any other type of support reactions. Now the free body diagram is complete, and we have exactly 3 unknowns, Ax, Ay, and Ma. Therefore, we can write the 3 equilibrium equations to solve for all of them. The first equation is the resultant force along the x direction, equals to our unknown force Ax minus the x component of the 1000 Newton force, and it equals to 0. Note that you must write the equation according to the coordinate system that you set up. In this case, I set right to be the positive x direction following conventions. Therefore, force Ax is positive, and the 3/5 times 1000 Newton is negative. The next equation I plan to write is for the resultant force along the y direction. But before I do that, I need to use a concentrated force to replace this distributed load. Since this is a uniform distribution with a load intensity of 80 Newton per meter for a length of 1.5 meters, therefore the resultant force of this load is 80 multiplied by 1.5, and its position is right at the center of this load. Therefore, the resultant force along the y-axis equals to unknown force Ay minus the resultant force of the distributed load 80 times 1.5, and then minus the vertical component of the 1000 Newton forces, and it equals to 0. Again, the signs of the forces are consistent with the coordinate system I set up. Lastly, we write the resultant moment equation. Note that you can summarize the moment about any arbitrary point, but you should always try to find the best point to do so, and the rule of thumb is trying to reduce the number of unknowns in your equation. For example, for this problem, it is best to summarize the moment about point A, because unknown forces Ax and Ay both have lines of action passing through point A. Therefore, they don't create any moment about point A, and therefore would not show up in your moment equation. Also, when writing the moment equilibrium equation, don't forget moment is actually about an z-axis that is pointing out and perpendicular to the xy plane. Therefore, positive moment creates counterclockwise rotational effect, while negative moment creates clockwise rotational effect. So, the resultant moment about point A equals to first the unknown couple moment at wall Ma minus the free negative couple moment 200 Newton meter minus the moment caused by the distributed load and minus the moment caused by the vertical component of the 1000 Newton force, and it equals to 0. Now we have 3 equations, 3 unknowns. We can solve for all of them. The solutions all have positive magnitudes, and that means they have the same directions as we assumed in the free body diagram. If the calculated result is negative, then it has the opposite direction as assumed. In summary, to determine what type of support reaction is associated with the support, here's the rule of thumb. If the support prevents the translational motion in a direction, then it exerts a force along that direction against the motion. If the support prevents the rotational effect about an axis, then it exerts a couple moment about that axis against the tentative rotation. Let's look at another example. Here's a member ABC subjected to the 3 kN force and 8 kN couple moment loadings as shown. It is supported by a smooth collar at point A, a rocker at point B, and a cable at point C. We are asked to determine the support reactions at these points. We need to analyze these supports and draw the reactions they exert on the free body diagram. First, let's look at the smooth collar at point A. We realize that it does allow movement along the rod, and because the member is pinned to the collar, the member is allowed to rotate either counterclockwise or clockwise. The only motion it prevents is along the direction perpendicular to the rod. Therefore, we can tell the force support is along that direction. It could be either in this direction or in this direction pointing to the right. Let's first assume it is in this direction. This is our first unknown force, Fa, associated with the collar. Then, let's look at the rocker at point B. It allows motion along the horizontal direction. It allows rotations as well. It even allows the member to move upwards. The only motion it does not allow is for the member to move down. It exerts a force vertical upward. Lastly, the cable at point C allows all motions except for when the member wants to move away. Therefore, the force of the cable is a tension force that pulls the member. Keep in mind that the force associated with the cable support is always tension force that pulls. You can imagine trying to use a cable to push. Now, the free body diagram is complete. We have 3 unknowns, Fa, Fb, and Tc. And we can write the 3 equilibrium equations and solve for all of them. Note that the calculated Fa is negative. This means that the direction of force at the collar A is opposite to what we originally assumed. Here's another example. We need to determine the support reactions at the roller and the pin. A roller is similar to a rocker or a simple contact support, and it exerts a force that is perpendicular to the contacting surface. A pin support allows rotation, but it prevents motion in both horizontal direction and the vertical direction. Therefore, the support reactions are 2 forces along these 2 lines. We can first assume them to be in these drawn directions. Now we have 3 unknowns. We can write the 3 equilibrium equations to solve for them. Note again, here we have a negative force, indicating the direction of this force is opposite to what we originally assumed.